A spam filter reads an email and marks it as spam. YouTube looks at viewing behavior and ranks videos. ChatGPT receives a prompt and returns text. These systems look different, but people call all of them artificial intelligence. That makes the first question harder than it sounds. What does the label AI actually tell us? Artificial intelligence is a broad category of computer systems. These systems take an input, process it, and produce an output for a task that involves prediction, classification, recommendation, generation, or decision support. A spam filter takes an email as input and returns a label. A recommendation system takes information about a user and a collection of videos, then returns a ranking. A language model takes tokens as input and produces probabilities for the token that may come next. This definition is useful because it names the parts we can inspect. What is the input? What process turns that input into an output? What output does the system produce? Who uses that output? And what happens if it is wrong? AI is not one program, one model, or one level of intelligence. The category includes systems built with explicit rules and systems that learn patterns from data. It includes narrow systems that do one task, such as detecting a suspicious bank transaction, and more general tools that can work with many kinds of text, images, audio, or code. The boundary also moves with time. Once a technique becomes ordinary, people may stop calling it AI and simply call it software. That is one reason a single timeless definition is difficult. For this course, we will use a practical test. An AI system uses a machine-based process to infer an output from an input for a human-defined goal. The output may be a prediction, a recommendation, a generated object, or a decision. Keep one sentence in mind. An AI system takes an input, transforms it with rules or patterns learned from data, and produces an output for a task. Suppose we want to stop spam. One approach is to write rules. If the subject contains certain phrases, add points. If the sender is on a block list, add more points. If the total passes a threshold, mark the email as spam. The programmer decides which clues matter, how much each clue counts, and where to put the threshold. The computer applies those instructions. This is a rule-based system. Large rule sets can support complicated behavior, and rule-based expert systems have long been part of AI. The weakness is maintenance. Spammers change their language. Legitimate messages may contain words that once looked suspicious. Someone has to inspect mistakes and update the rules. Machine learning changes who sets the internal decision rule. People still choose the task, collect examples, define the target, and choose a learning method. The system then adjusts model parameters to fit patterns in the examples. For a spam filter, the training data might contain emails labeled spam or not spam. The learning algorithm looks for parameter values that reduce prediction errors on those examples. The result is a model. A model is the structure and parameter values needed to map a new input to an output. The word learning can sound more human than the process is. A machine learning model does not attend a class or form a personal understanding. An optimization procedure changes numbers inside a mathematical function. If the training process works, those numbers capture regularities that help on new examples drawn from a similar setting. This distinction explains much of modern AI. Traditional software often starts with rules written directly by a programmer. Machine learning starts with data, an objective, and a model structure. Training finds parameter values. After training, the model applies those values to new inputs. The two approaches can also work together. A bank may use a learned model to estimate the probability that a transaction is fraudulent, then apply an explicit rule that blocks transactions above a chosen risk threshold. The model produces a score. The rule decides what action the system takes. Real products often combine models, rules, databases, and human review. Training and inference are two different stages. Mixing them up makes AI seem more mysterious than it is. During training, the model changes. During inference, a trained model is used to produce an output. Return to the spam filter. We give the training program an email and its correct label. The current model produces a prediction. A loss function measures how far that prediction is from the target. An optimization method adjusts the model's parameters so that future predictions can have a lower loss. The process repeats over many examples. This does not mean the model simply stores one rule for every email. The goal is to find parameter values that work on emails it did not see during training. That ability is called generalization. Generalization has limits. A model trained on one distribution of emails may perform poorly when the language, users, attackers, or data source changes. Good performance on the training set is not enough. Developers use separate validation and test data to estimate how the model behaves on unseen examples. They also test important subgroups and failure cases because one average score can hide a serious problem. After training, the parameters are fixed for normal use. A new email arrives. The model processes its features and returns a spam probability. That forward use of a trained model is inference. Inference may happen thousands or millions of times after one training run. It is usually much cheaper than training, although a large model can still require substantial hardware for each request. Here is the clean distinction. Training uses data to change the model. Inference uses the trained model to process new data. Some systems continue learning after deployment, but that is a design choice, not a property of every AI system. A chat model does not normally rewrite all of its base parameters because one person sends a message. The conversation can change the context used for the next response without changing the underlying trained weights. This also separates a model from a product. The model performs a learned mapping. The product may add a user interface, search, memory, safety rules, external tools, logging, and human approval. When people say an AI system did something, we need to ask which part produced the result. Machine learning includes many kinds of models. Deep learning is one family within machine learning. A deep neural network contains multiple processing layers. Each layer transforms the representation it receives. Training adjusts the parameters across those layers so the network can produce useful outputs. Consider an image classifier. The input begins as pixel values. Early layers may become useful for detecting local patterns such as edges. Later layers combine simpler patterns into more complex representations. The final layers use those representations to produce scores for possible labels. The network is not given a human-written rule that says, first find this exact edge, then find this exact shape. The useful intermediate representations are learned as the full network is trained for its task. Backpropagation makes that training practical. The model produces an output, the loss measures the error, and backpropagation calculates how changes in each parameter would affect that loss. An optimizer then updates the parameters. Repeating this process over data gradually changes the network. The word neural comes from a loose historical inspiration. An artificial unit in a neural network is a mathematical operation. A modern network does not reproduce a human brain. Calling it a brain hides the mechanism we can actually describe. Layers of numerical transformations, learned parameters, and an objective used during training. Deep learning became important because these layered models can learn useful representations from complex data, such as images, audio, and text. The price is that they often require substantial data and computation, and their internal reasoning can be difficult to inspect directly. Large language models are deep learning models built to work with language. Many modern generative LLMs use a transformer architecture and an autoregressive training objective. Start with the input. The model does not receive a sentence as a human idea. A tokenizer divides text into tokens. A token may be a whole word, part of a word, punctuation, or another text unit. Each token is represented by numbers that the model can process. Now, take a short sequence. AI can help us. The model processes those tokens and returns a probability distribution for what might come next. It may assign one probability to learn, another to solve, another to write, and small probabilities to many other tokens. Generation selects a next token according to a decoding rule. The selected token is added to the input. The model runs again, and the process repeats. One token at a time becomes a sentence, a paragraph, or a block of code. Those probabilities are learned during pre-training. An autoregressive language model sees large amounts of text. At each position, it tries to predict the next token from the tokens that came before it. The actual next token provides a training target. Prediction error changes the model's parameters through optimization. This task sounds narrow. To predict text well across many subjects, the model benefits from representing grammar, word meaning, style, common associations, and patterns that appear in explanations, arguments, stories, and code. Those representations are distributed across many parameters. They are not a clean list of facts that we can open like rows in a database. The transformer helps the model use context. Its attention operations compute how information at different token positions should contribute to a new representation. In a sentence with a pronoun, information from earlier words may help shape the current representation. In code, a name introduced many lines earlier may matter for the next token. Attention does not prove human understanding. It is a specific numerical operation on vectors. Pre-training produces a base language model that is good at continuing text. A useful assistant needs more. Instruction tuning trains the model on examples of prompts and desired responses. Other alignment methods can use human preference data to make some responses more likely than others. The exact recipe differs across models and companies. This is why a chat assistant is not explained by the phrase next token predictor alone. Next token prediction describes a central training objective and the token-by-token generation process for many generative LLMs. The behavior users see also depends on the model architecture, training data, scale, instruction tuning, preference tuning, system instructions, tools, retrieval, and decoding settings. It also explains why the same model can appear to do many tasks. Translation, summarization, question answering, classification, drafting, and code completion can all be expressed as text in and text out. A general language interface lets one trained model respond to many task descriptions without creating a separate user interface for each task. The model may also use information placed in its current context. A prompt can contain instructions, examples, or documents. The model processes that context during inference. This is often called in-context learning when examples in the prompt change the pattern of the response without updating the model's parameters. Tools extend the system further. A language model can produce a structured request for a search engine, calculator, code runner, or database. The external tool returns a result, and the model uses that result in the next step. The language model did not acquire a new permanent fact from the tool call. The surrounding system supplied information for the current task. Fluent language is not the same as verified information. An autoregressive language model is trained to assign probability to token sequences. A likely continuation can be accurate. It can also be false, internally inconsistent, or unsupported by the input. NIST uses the term confabulation for generated content that is confidently wrong or that conflicts with the prompt or earlier output. Hallucination is the more common informal term. This failure is easier to understand once we separate generation from verification. The model can produce a sentence because its token pattern fits the context. That process does not automatically check the sentence against a trusted database, an experiment, or the physical world. Verification must come from somewhere. A retrieval system can provide documents. A calculator can check arithmetic. Code can run against tests. A human can compare a claim with a primary source. These checks belong to the complete AI system, not to fluent text generation by itself. Models also inherit limits from data and design. Training data may be incomplete, outdated, unbalanced, or wrong. A prompt may leave out needed context. The system's objective may reward behavior that does not match the user's real goal. A model that performs well on one benchmark may fail after the setting changes. So, intelligence is not one score that a system either has or does not have. Ask what task the system performs, what data and objective shaped it, how its output is evaluated, and what happens when it fails. We can now return to the 3 examples. The spam filter predicts a label. The recommendation system ranks options. The language model predicts tokens and may sit inside a larger assistant that also uses instructions and tools. All are AI systems, but they solve different tasks with different models, data, outputs, and risks. The next lesson will focus on one step we only introduced today: how machine learning changes model parameters from examples. Later courses will separate algorithms, large language models, practical AI workflows, mathematics, system building, and reliability. Each course answers a different kind of question. For now, keep the working definition. An AI system takes an input, transforms it with rules or patterns learned from data, and produces an output for a task. Understanding any AI system begins by identifying those parts and checking who depends on the result.